Welcome to Chapter 1 of the Introduction to Statistics. Our main goals here are to introduce what statistics are, how we might want to use them, and in our case specifically how they apply to psychology. Also, we'll talk about some of the basic terms and concepts we'll definitely need to be familiar with because a lot of the stuff in this chapter, while maybe not conceptually terribly difficult to start things off, will be in many ways the bedrock for how we build up more complicated and more fun things later on throughout the semester. I thought this was a sort of funny way to get going because maybe not everyone is excited to learn about statistics on the first day, but I think there are some fun things we can do with statistics, and we can have fun in this class and enjoy the process, but also sometimes we can get bogged down a little bit with formulas, with notation, but it's also important to remember there's a good reason why we spend our time to learn this, because in many ways, our first way of thinking about problems is not necessarily from a statistical perspective, especially when we talk about probability. But in many ways, that's a lot of how life works. It's not definite yes or no answers to a lot of the questions we have. It's about what is the probability that if we try this food, if we buy this product, it will make our lives better in some way. So once again, we don't live in a world of guarantees, and so we have to accept that many of the answers to questions we ask have to do with probability, and we have to live with a little bit of uncertainty when we enter the world of probability and statistics. For each chapter, I like to go over an overview that organizes some of the key things that we'll be talking about. Here you can see we are first going to talk about statistics, some scientific method and observation issues. You've probably covered the idea of populations and samples before, but it's important that we spend plenty of time being familiar with these concepts. We're also going to talk about some different types of research and study designs. So we're going to review a little bit about what we probably already know in terms of what a correlation is, what an experiment is, and the different parts of an experiment, and why it's important to be very familiar with those, because a lot of the statistics and the statistical tests we'll learn about in this class are basically identifying what kind of variables we have. So that gets us into our next section. How do we know what kind of a variable we have? Why is it important to know that? Well, a lot of times it leads us into, if we have this kind of variable, continuous versus discrete, for example, we'll learn about that in a little bit. Once you know what kind of variable you have, that will lead you into what kind of statistical test is most appropriate. And a lot of times, the types of variables you have are also a product of the kind of research study design you have. So for an example, a lot of times experiments involve more discrete variables. Either you're in the control group or the experimental group, whereas correlational research often involves more continuous variables, a whole range of values, and you just see if the range of one variable is related to or correlated with the range of another variable. I'm being a little abstract here, but it'll make more sense once we get to those concepts later on. And then finally, as part of getting in the door in statistics, we need to learn about statistical notations. So it's very important that we learn how to label statistics properly. This is where we might start thinking about statistics as a language, and we're translating maybe how we'd want to discuss or explain in our native language how these numbers relate, but we also need to translate that into statistical language, which involves notation, sometimes formulas, sometimes big letters, sometimes italics. So it's a little picky, but it's also crucially important so that we're all speaking the same language of other people learning statistics across the world, that we know our notation and are comfortable using it. So let's first talk about statistics and generally science, and what does it mean to do observation about things in our natural world. First, we might want to ask ourselves, What are statistics? We might have a common definition, which is basically that it's numbers, and sometimes the numbers are organized into tables and graphs and charts. And that's true. That's not wrong. But we're going to go a step deeper. And as far as a researcher or a more academic definition, it is a set of methods and rules for organizing, summarizing, and interpreting information. So notice we've set out a three-goal setup for thinking about statistics. It helps us to organize, it helps us to summarize, and it helps us to interpret. And it also provides a standard way of doing these things so that I can read research of statistics that are done by people in languages that are not English. So if they had to listen to them describe the conclusions of their statistics, maybe I wouldn't understand the words they're using. But since we're all using the same set of rules and notation and formulas, I can understand that. And so it's a big part of translating maybe how we understand the world in our spoken language to the language of statistics. Let's also discuss what is data. So it's not Lieutenant Commander Data from Star Trek. We're getting nerdy here already earlier in the class. But data is a set of measurements or observations. And that's a pretty wide definition. And it doesn't always have to be numbers, but in our case, we're going to pretty much use only numerical kind of data. It's crucially important that we discuss populations versus samples, that we know when we are talking about or referring to a population versus when we are talking about or referring to a sample. So what do we mean by these concepts? First of all, a population is all individuals or scores of interest. This is, if we're doing a study, we probably don't just care about the people we get data from. What we really care about is all the people that are like or affected by the data that we did get. Now, if we're trying to understand a group or a population, why don't we just get data from the whole population? In fact, that would be the ideal way to go. If I wanted to know, for example, what is the working status or employment status of every adult in the US, it would be great to have information from every adult in the US. The problem is we can't get that information. We likely don't have it. There's going to be missing data. There's going to be parts of that population that we just can't get. So what we have to do is make a compromise. And that compromise is the sample. So this is a subset of people from the population that we care about that we actually do get data from. And we're going to talk about a bunch of ways in which when we do a sample, we have to ask questions about, is this sample representative or like the population that we really care about? So first of all, we have to be careful in specifying our population. If we're doing research, do we just care about males, for example, or females only? That means that once we collect our data and make conclusions, our conclusions should only apply to the population that we care about. So we can't do research for a drug for male pattern baldness and then expect it to work for females, right? So we need to be clear about what our target population is ahead of time so that we don't overextend it later on. And then we need to be careful about getting a representative sample of that population. So for example, if we're studying male pattern baldness again, we are looking at males as our target population. Now we want to get a sample of males. What if we just get a sample of people from a commercial who call this number and we'll give you a free trial product? Well, that might be a biased sample because out of the whole population of people that have male pattern baldness, maybe only a certain percentage of that are actually watching our commercial, and even a smaller percentage of that are actually willing to call the number and put in that effort. So there are a lot of reasons why a sample is an imperfect compromise for trying to get a a representative sample from a population. So we have some examples here. Sampling is something that we deal with all the time in social sciences and science in general in our life. So for example, all women, population or sample, that would probably be a target population. Now if we usually have just one number, unless that represents all our population and we don't have any information that it does, this would be a sample of 500 women. All college students, think about the millions of college students. Could we get data for each person in this population? Probably not. So this is our definition of a population, but we'd probably have to compromise by getting a sample. Also, we have a classic example of a study and a certain number of participants in that study, or a sample of participants. Now the students in this class, is that a population or a sample? Well, if I only care about what's happening in this particular class, then it might be that this is the only population of my interest. But if, for example, I want to infer that things that happen in this class will also likely happen in future classes, then I would be treating this class as a sample and using what I have learned about this class to make inferences about other classes. So the other classes, future classes, would be my population, all students I would ever teach in quantitative methods in psychology, and then the sample would be just the people in this class that I interact with. Finally, it's hugely important to distinguish between parameters versus statistics. So first of all, the statistic is just describing the sample. So when we're talking statistics, we're already talking about how we're thinking larger about a population, want to make inferences about a larger population, but we only have data from a sample. And that data we're going to call from that sample our statistics. Now, if we want to think about the larger population, that is referred to as a parameter, a population parameter. So it's nice that these terms both line up with the same letter, sample statistic versus population parameter. That should help you to remember them. Sometimes we have actual parameters for an entire population. Let's say I own a company and I can have everybody's salary data for the entire company. That means I have the parameter of my population of people who work for me. So sometimes we have that number that we know is true. Other times we don't have data from everybody in a population and we have to estimate the population parameters. So again, once we go into estimating or guessing, there's good rules for how to do that the right way, but we are making a compromise when we do that, and it's important to be aware of that. So much of our statistics that we're going to learn about in this class deal with situations where we don't know the population parameter and we have to try and figure it out and guess. One way to look at how these concepts relate is this cyclical interaction. So basically we have our target population. This is everyone that we think would be affected by the results or represented by the results of our study. And of course, in most cases, we can't get the whole population, so we need to get a sample from the population. We have to determine the procedure for the sample and try and give everybody as close of a chance to be involved as we can, so we're not just being biased and selecting only our friends or only our gender or only young people or old people. We want to get as close to a random pull from the population of the sample that we get. And of course, that once we get the sample, now we have data and calculate statistics that summarize information about that sample. And then of course we circle back because we started with caring about a population of interest, and then we have to think about the sample we got, the data we got, the statistics we have, and think critically about how well our statistics are likely to generalize to the larger population that we really care about trying to figure out. Continuing on this distinction between populations and samples, we have two primary categories of statistics. First of all, we have descriptive statistics, and this simply goes to that bottom part of the circle from the previous slide. We have our sample. Descriptive stats tell us about that sample. So for example, if we have manager X and the people who work for manager X, we can get descriptive stats to talk about and organize and make inferences about what's going on with this particular manager's subordinates. However, we may not want to just use that data to make conclusions about the people in that sample. As we talked about before, a lot of times we might want to use that sample to make inferences about a larger population. Again, a population that we don't actually have data for, but we want to use our sample data and our sample statistics to make inferences about the patterns we see in our sample and think critically about whether those patterns apply to the larger population. So instead of just the people that work for manager X, what if I use those results from that sample to infer what people who work for managers like manager X, a larger population, might be about? As you can see, there's going to be a discrepancy between a sample and a population. We're making that compromise. We can't get all the data points from an entire population, and we can only get a sample of that. And that difference is what we're going to refer to as sampling error. Sampling error is something that is going to come up over and over throughout this course because it's something we know is there, and we don't know exactly how much sampling error there is. So a lot of our statistics are trying to account for this and figure out how can we come up with the best guesses about how much sampling error there is, or how much potential difference there is from what our sample statistics are telling us compared to what the population parameters are. And again, most population parameters we don't know. So we can't just say, well, this number differs from that number. It's we have a number from our sample and we're guessing about our population, but don't know for sure, and trying to guess how similar or different our sample data is from our population values. So as you can tell, it's some pretty difficult questions conceptually that we're already digging into in this first chapter. So one example here to illustrate the concept of sampling error, let's say we have a college that has 1,000 students and we only care about those 1,000 students. That is our target population. We're not trying to use any data from, in this case, any data from this college to generalize to what might happen at other colleges. This is our target population that we're trying to understand. In this case, we actually know the population parameters. Let's say we've got data about age, IQ, and gender for each of our 1,000 students. Okay, so in this case, we do know the parameters. But let's just assume that if we wanted to take samples, right? In this case, sample sizes of 5 people in sample 1, 5 people in sample 2, 5 people in sample 3. Notice how the average age, IQ, and gender breakdown is not the same based on these samples. They don't match each other. First of all, sample statistic 3 versus 2 versus 1, and those statistics don't exactly match the population parameters. So this is a situation where we know we face in a lot of the statistics we do. So how do we deal with it? Well, you can probably see, first of all, that a sample of 5 people is pretty small. And what we're going to find out is that when we have larger samples, typically that's when our sample statistics are more likely to match the actual population parameters. So let's imagine if instead of a sample of 5 people, we had a sample of 500 people out of our population of 1,000, chances are what we'd see are these numbers would be much more similar to our overall population parameters. So just some things to think about in terms of populations versus sampling, and what kind of factors are likely to make sampling error larger, sample size being small, and what circumstances are likely to make sampling error smaller or a larger sample size. There's other factors too, but sample size is one of the biggest determinants of how much sampling error there is. So you might ask, why do we need descriptive and inferential statistics? So first of all, imagine if we had a research question, which is, 2 teaching methods, do they differ from each other? So this might be a classic experimental design. We take a sample and randomly assign the students to 2 conditions. One gets teaching method A, the other gets teaching method B. Okay, so and this would be an experiment to compare 2 teaching methods. And we could even say our population. It's not all students. Let's just say we're limiting our target population of this teaching technique to first grade children. We're not going to assume that anything we learn about this would apply to high schoolers. Now, let's say, based on that simple experimental design we covered in the last slide, we look at average test scores. So we have our teaching technique, technique A, technique B, and we have our 2 groups, the class that got A, the class that got technique B. And now we have some sort of outcome. Did that teaching technique cause or affect change in something important? And so now we have the outcome variable of test scores. So did our teaching technique cause a difference in test scores for the classes that got the different techniques? And we see an average score of 76 test score for sample A, 71 for sample B. So we see a different average, but notice not everyone is right at that average. There's some variability around that average point. So our descriptive statistics are summarizing the data in our sample. Okay, so that means if we're thinking in a sample statistics perspective, we're saying this average represents sample A. And can we conclude that sample A is higher? Yes, it is higher, but is it meaningfully higher? Well, we're going to find out that we can't just consider the average, right? We know that the average is higher, but look at the spread out around the average. So we're thinking in terms of both central tendency, in this case mean, versus also we have to consider the standard deviation in this case, or the spread out around that average. Now another thing to consider is that we're talking about sample statistic. Is the sample statistic of a mean of this teaching technique different from this teaching technique? Let's say we wanted to do inferential statistics. How is our research question changing? Well, in this case, we're not just comparing the 2 classes and saying, well, this class did better than that class. We'd also be saying, can we infer that that pattern applies to the larger population of not just the first grade student sample we have, but first grade students all across the state of Ohio, for example. And that's the difference between thinking of statistics in a sample versus taking sample statistics and inferring them to represent patterns that could apply to the larger population. And of course, that seems like a little bit of a stretch. We're probably not quite ready to do that just yet, but we're going to kind of build up the pieces to allow us to do that moving forward. Why do we need descriptive statistics? Once again, we can see that one group has a higher average. we can make two basic conclusions. There's no difference. We can say, for example, 76 is higher than 71, but not big enough for us to consider important or meaningful. Or we can make the other conclusion, right? That this difference between 76 and 71 is meaningful, right? Now, how do we fold sampling error into? Well, maybe if we think there's a lot of sampling error, maybe a really small sample size for both Class A, Class B, especially with those small groups, maybe we're just not sure that this difference is likely to hold up, right? But maybe we have information that we think this difference would hold up if we apply it to the larger population. And once again, what kind of information would I like to think that that information or that difference would hold up? If they were big classes, lots of students, and that difference, to me in that case, would have less sampling error, and I think more justification to infer it to a larger population. But in this case, how do we know which is correct? We don't have our sample sizes. We don't know how much sampling error is in there. That's why we need to think about inferential statistics, and if we're going to make these inferences, we need to know more information before concluding that this mean difference is important, or not just due to sampling error. Let's take a step back and look at some research study design. First of all, we have to think about what is a variable versus what is a constant. As we can see, a variable is something that is not going to be the exact same for a sample or a population. So variables are things that we see every day. If we look at physical features, blue eyes versus brown eyes versus green eyes, hair color, height, skin color, cardiovascular health, no two people are going to be alike, most likely on all those things, and certainly not everyone's going to be the same. So those are all variables. Now, what is a constant? Let's say for this sample of people in this class, we're all registered for this class. We're all the same. Another one would be that I've used in classes before. Imagine a simple survey that says check alive or dead. Well, everybody here is alive. Everybody here has a pulse. That's constant. So if we're all the same on something, it's really not telling us that much interesting, right? So that's something to keep in mind. What we really care about are variables, but sometimes we have to fold in constants or consider them as well. So the basic goal of research studies is just to say, these are some variables that we care about. How are they related? So you can see those lead to some more questions that maybe we're familiar with and familiar ways of thinking about our social and human world. So for example, do parenting styles versus permissive versus authoritarian, influence or sometimes cause a difference in children's grades? Does confidence lead to better performance, whether it's on the job, whether it's at a hobby or a sport? So those are thinking about variables. Of course, we're all going to have different levels of job performance or sports performance. We're all going to have different levels of confidence. Those are clearly variables. Then the question is, are they related to each other? So let's look at some research study designs. How do we extend this basic question of wanting to know the relationship between variables to how does that lead to the kind of study we need to set up? So first of all, we have the observational or correlational method. So first of all, and this is a review from Intro Psych and perhaps other statistics you've had before, this is observing variables in their naturally existing state. That makes sense for the observational method. Correlational method is just measuring them, specifically putting them in a numerical state. So with the correlational method, I often think about you have a bunch of columns and rows in a spreadsheet, right? Once you have that spreadsheet set up and you have those numbers put in there, you can just point, click, and shoot, as we'll see with statistical software this semester, and calculate the correlation between any of the variables in that data set. And the key is You haven't controlled anything. All you've done is measure them as they naturally exist. And we'll talk about types of variables, but typically the correlational method, we want to have continuous variables, although there are some methods that we might be able to do correlation-like things, a version of what we're going to learn later on as chi-square, for non-continuous variables. So just throwing these terms out there so we start to get familiar with them early on in the class. How is the experimental method different from the correlational method? Here we are manipulating variables of interest. So for example, with the correlational method, if I wanted to know if there's a relationship between how much caffeine you consume and the quality of your sleep, I just have a survey asking how much caffeine do you consume a day? What is the quality of your sleep? The experimental method, on the other hand, says we're going to manipulate one of those variables, especially the one we think that is doing the causing. So in the caffeine and sleep example, I would think that a lot of caffeine throughout the day is going to have a negative impact or cause lower quality sleep. And instead of just letting you, in an experiment, choose whatever caffeine you want to consume, in that case, I would be manipulating your caffeine intake. I'd be saying there's a two-group, control group, and experimental group conditions, and I'm going to randomly assign you as a participant in my experiment to either of those groups, being a high caffeine consumption group and a low caffeine consumption group. So instead of choosing yourself how much caffeine you normally want to consume in the correlational method, the experimental method means I am controlling that as the researcher. The experimental method allows us to make inferences about causality because we've manipulated that thing we think is doing the causing. Whereas correlations, it's important to remember, I'm sure you've heard this before, just because two variables are correlated does not mean that from that correlation alone you can infer one causes the other. You could further test that with an experiment and find out that one variable does cause the other, but you can't make that conclusion just with the correlation. You need the experiment. So a couple things to consider with the experiment is that when you have your sample who is going to participate, then you randomly assign them to your different experimental conditions. You don't get to choose whether you're in the high or the low caffeine group, for example. That decision is made for you and hopefully randomly. Names in a hat randomly draw to the high caffeine or the low caffeine condition. And then the other thing is that since we've spent so much effort to manipulate that one variable of interest, caffeine consumption, for example, what we want to do is control any other potential difference variables and hold them constant. We don't want those to confound the primary relationship that we're trying to look at, which is caffeine consumption and sleep. So that means every other thing in the experiment besides how much caffeine you're consuming, I would want to hold constant or the same. So I try to, in this experiment with caffeine, for example, make sure everybody's eating the same amount of calories, eating the same kind of food, consuming the same kind of beverages and amount of beverages, that they're sleeping in their bed and not traveling, any other confounds that might mess up the primary relationship I'm trying to examine. So with an experiment, it's important to, and I know this is going to be review, think about the independent variable, which is the thing that we think is doing the causing. This is what we actively control or manipulate. And then we have the dependent variable, which if there is a causal relationship, changes in the independent variable cause a change in the dependent variable. So your sleep quality is in part dependent on your caffeine consumption, is the conclusion we could reach if we did that experiment. Also, as a review, the experimental condition gets the experimental treatment, the real drug. The control condition usually gets a placebo or a sugar pill or something that doesn't actually have the real active ingredient. Sometimes the experimental condition can be a new type of treatment compared to the previous treatment to see if there's a difference. And one thing to keep in mind that I go over in my intro psych classes is when we have an experiment, what is the contrast to show that something causes a change in something else? So for example, a drug. Does a drug cause lower depression in a sample of people who are depressed? Why don't we just give people the drug? And if people who take the drug feel better, we conclude that the drug works. Well, we have to control for what's known as the placebo effect. Basically, if people take a drug and they know it might be a real thing or might be a sugar pill, but the fact of actually taking that thing, even if it's doesn't contain the active substance, the placebo effect shows that people will think that it changed them in some way. So just giving people a sugar pill that might you lead them to believe might help with their depression, they're going to report that they feel less depressed. Okay, and that could just be due to the placebo effect. So what we need to do is have an experimental and control condition, people both taking a pill, and they're both going to have that placebo effect, feeling better just because they've taken the pill. And then if the experimental condition has even less depressed symptoms after taking the pill, we know that we then can conclude that the drug reduces depression beyond what is likely to be observed from just the placebo effect. Let's look at some research study design. So for example, we have a maybe less psychology-based example between severity of road conditions, one variable, and accident rates, another variable. What are the independent and dependent variables? What's doing the causing and what is the outcome? Well, our IV is going to be the road conditions, and we can be very specific about how we measure those. What kinds of things do we include in our road conditions severity measurement? And of course, the road conditions we would hypothesize would cause accident rates. And so, with any experiment, maybe we would manipulate road conditions. Some people are driving on a clean road, other people are driving on an icy road. However we want to set up our experiment, we would want to control for any other external potential causal variables. We want to hold those the same so that they don't act as confounding variables. They don't confound our conclusion about the primary causal relationship that we're going to look at. So first of all, what is the confounding variable about the road conditions and accident rates? Well, what kind of car are you driving? In our experiment, we're not just going to let people drive whatever car they choose. We're not going to have some people driving motorcycles and other people driving big SUVs. Everybody drives the same car, so we can't say that smaller car or two-wheel versus four-wheel confounds our causal or primary relationship that we're investigating. So you can think from there about a ton of other primary confounding variables that we want to consider in an experiment such as this. Another important thing to think about throughout the semester is that we have measurements, which are the numbers that we actually put in our spreadsheets. But in many things, especially psychology, we're dealing with abstract concepts. So things like personality traits, intelligence, abilities, things like self-esteem, ambition, humor. It's something that we know you can define about a person, but you can't directly measure. So even intelligence, right? We use IQ as the number, the measurement, and we know that's useful. It's correlated to a lot of things, but we know any IQ number is far from a perfect representation of what's really inside someone's brain. Okay, so that's the idea of a construct. Is we have sort of this abstract thing that resides within somebody, and this is often common things in psychology. Many other types of hard sciences would say, well, your constructs are so difficult to measure, you're not getting enough bang for your buck by all this work, so we're not even going to concern ourselves with those things. But in psychology, we say, yes, even though we can't measure personality or intelligence even close to perfectly, we can do it well enough to be useful. How do we do it well enough? Well, we have an operational definition. And that's basically, we're saying, we're trying to get this construct as best we can, knowing we can't just go into someone's brain and get their exact IQ. But here are the things that we think are part of that construct. So these are certain parts of this abstract thing we're trying to measure, that this is where our numbers are coming from that we can observe, and we know they represent that internal thing about our brains or our personality imperfectly, but we still think they're useful, and we spend a lot of time to at least make sure that our operational definitions are close to or representative in some way of the abstract construct. So in this case, self-esteem might be the abstract construct. How can we measure that? Well, we could do a survey. We could do something like number of friends. We could do something like number of hobbies. None of those are perfectly going to represent the construct of self-esteem, but we can make the argument, and then we have to test that through doing statistics and studies to provide evidence that those things are useful and related to what we think of as self-esteem. We've previewed these concepts before, but now we're officially introducing them. So first of all, we have what we consider a discrete variable. This is where typically, like a coin flip, it's either heads or tails. This is usually also a yes or no answer, sometimes gender, male, female, although now we're starting to think of gender as less of a discrete construct than before. Whereas continuous, this is where, unlike a coin flip, there can't be 1.5 heads. It's either a head or a tail on the flip. Continuous variable means we can have a number of possible values in between the observed values, right? So let's say I measured your height or your weight, and we get your weight in pounds, your height in inches. Well, you're not exactly that number of inches or that exact number of pounds. We can even subdivide that further. You're 1.238 pounds, for example. And that is what conceptually is the difference between a discrete variable and a continuous variable. We can take what we know about the difference between discrete and continuous variables even further and come up with our scales of measurement. This is going to be hugely important for us as we move throughout the semester, because once again, if you have data that is measured on one scale, that's going to lead you to a certain type of statistical test, whereas other scales are typically used in other types of statistical tests. So first of all, we have what's known as a nominal scale. These are just categories. There's no real way to organize them from bigger to smaller. So for example, I've got Burger King down here as one categorical measurement. You're either at Burger King or you're not. And Burger King is different from McDonald's, which is different from Taco Bell, but it's just in terms of the name. There's no necessary way that you would order those categories. So you don't get a whole lot of information from a nominal scale. But oftentimes, if you think about maybe an experimental versus control condition, that might be a nominal scale. Next up, we have an ordinal scale. So these are categories that you can organize from often smallest to largest. So here I have the example of French fries, right? So you can order a small, a large, or a medium, or an extra large, and you know which one is going to give you more or less fries than the other one. But here's the tricky part. just because you know one's bigger than the other, you don't know exactly how much you get. And this is something that we're dealing with now with our economic conditions of shrinkflation. McDonald's can have a supersized fry that has less fries than it did 2 years ago, but their supersized fries is still going to have more fries than their large and medium and small fries. So the ordinal scale is useful in terms of organizing things in an ordered sequence, but it doesn't tell you how much of the thing you have. And these types of variables are often known as our discrete variables, going back to our previous slide. You're either getting the large or the extra large. There's no in between. You can't order a half of an extra large. Similar with Burger King. You're either eating at Burger King or you're not. There's no in between. Now we move into more continuous type of variables. So in this case, we have the same ordering effect, but now the intervals between the categories are the same size. So this is when we start to think about the actual numbers. So it's moving from ordinal, we're thinking about big versus medium versus little. Intervals, now we're looking at numbers. We know the difference between 1 and 2 is the same as the difference between 2 and 3. And the same logic applies to what we know as a ratio scale, except that with a ratio scale, we now have a true zero. So oftentimes things with hard science are in ratio scales. There is a absolute zero in temperature, for example. If we're dealing with money, we know there's an absolute zero here. Now, interval scales are often more appropriate for our psychological constructs, such as intelligence or ability. Chances are no one has a vocabulary ability of 0. And so if we assume that anyone who's alive has a more than 0 vocabulary ability, we can't say that that's a ratio scale. It has to be an interval scale. And of course, once we put numbers to our SAT, even though there's no true 0, we know that the difference between SAT of 600 and 610 is the same interval as the difference between 610 and 620. So again, nominal ordinal scales are more discrete, and our interval and ratio scales are more continuous. As we start to wrap up, it's important to look at some statistical notation and also start thinking about numbers in terms of formulas. So typically we have our IV in experimental framework as an X, and a dependent variable is a Y. Now, it doesn't have to be this strict experimental thing if we're thinking more in a correlational setting, or especially when we talk about regression. We usually talk about X variables as more of our predictor variables and Y variables as more of our outcome variables. Now we have what's known as an N size. Big N is our population size, number of scores in the entire population. Sometimes we know it. We know our entire population. Other times we don't. But with our sample, we do know the size of our sample. So little n is always going to tell us the size of our sample. We also have our sigma sign. This is adding up all of the values following the symbol. So we're going to deal with sigma a lot throughout the semester, so let's get comfortable using sigma. So for example, sigma x, we would add all of these x values together. So sigma x is calculated by adding these together, and then our answer for sigma x is 56. So what is our sigma y if we did that? Well, we would add up all these numbers, and what would that give us? Looks like 12 to me, if I'm doing my math correct. So sigma y would equal 12. And depending on your background, a lot of the stuff we're doing may be review, or it may be stuff that you didn't know very well, or it's been a long time since you've done it. So just as a quick review, we're going to go over the order of operations. Anytime we're dealing with formulas, we have to know what do we do first and what's the order of what comes next and what comes next until we've completed the formula. So we have the PEMDAS acronym that helps us as a guide to what to do first, parentheses, then exponents, multiplication, division, addition, and subtraction. So how does that look? First of all, we have the mnemonic device for PEMDAS. Please excuse my dear Aunt Sally. You may have heard that one before. And if we apply this to a formula, what are we going to do next? So first of all, parentheses. We got to figure out what's in this parentheses first. And within this parentheses, then what do we do next? Well, we have to do the multiplication first. So 6 times 7 first, plus 5. Then we can do our exponent, because we've done what's in the parenthesis first. So 6 times 7 plus 5 squared, and then times 3 gives us our answer. Okay, so we'll have some practice using the order of operations moving throughout the semester. So that wraps up what I wanted to cover for this introduction to how to think about statistics and what's going to come. Looking forward to hearing any questions, comments, thoughts you have in the discussions, and we'll have more next week.